Hello and welcome to Physical Attraction. This episode in our Fusion Odyssey we're going to talk about the challenges facing the world's largest fusion experiment, ITER. Where we last left magnetic confinement fusion, we were talking about the achievements of JET and other tokamaks around the world, getting closer than ever to break even and discovering new modes of operation such as the H mode that improve plasma confinement. The ITER, that stands for International Thermonuclear Experimental Reactor Project, will take the story of tokamak fusion reactors right up to the present day. And, as I write this, you can still get daily updates on its construction, and the machine is due to begin fusion experimenting in earnest in 2025. In the grand scheme built up by today's fusion glitterati, ITER is intended to be the last purely experimental magnetic confinement fusion reactor ever built. The plasma in ITER will undergo ignition and sustained burn, and it will generate 10 times as much power as is supplied to the plasma, demonstrating once and for all that magnetic confinement fusion can be used to release energy. Studies from ITER will then determine the practicalities and necessary design specifications of the first ever magnetic confinement fusion power plant, which will actually supply power to the grid. This will then attempt to overcome all the various barriers, problems and inconveniences with actually using the energy released by fusion in a practical power plant. And perhaps on this timeline, by 2050 or 2060, fusion power might finally supply energy to the grid and begin the long, arduous process of learning to be cost competitive with the alternatives that exist out there right now. Because ITER is the plant that is supposed to demonstrate the feasibility of fusion with tokamaks, and because it has taken so long to build and cost so much and required such a large international collaboration, the stakes for ITER have always felt very high. If ITER, like NIF before it, is judged to have perhaps failed in its primary scientific goal of achieving plasma ignition and break-even, or if it does so in such a way that makes it clear that fusion plants won't be economical in the future, then it's incredibly difficult to see how another unprecedentedly large tokamak will be built. That doesn't of course mean the end of fusion power, or efforts to pursue it, or even science in tokamaks, but it's difficult to imagine how chilling the effect would be. And in all honesty, we'd then be relying on something unexpected to come out of a startup, or a national fusion project like the ones in China that are quite secretive, to have any prayer of realising fusion power on the grid within our lifetimes. Even if the ITER timeline is correct, I'll be in my late 50s or early 60s before any power from fusion gets to the grid. In this episode we're going to talk about the history of the ITER project, and some of the challenges that it faced and will continue to face in the future. On this show we've talked before, particularly in some of the Nobel Prize episodes, about how science, especially experimental science, is becoming a huge collaborative endeavour. In many ways this is the price of progress. It's much more difficult for individuals to do truly groundbreaking research in their back gardens, simply because of how much we've already explored. In that sense it's possible that ITER is the world's biggest science experiment. 35 countries, representing over half the world's population, from the European Union, the US, China, India, Japan, South Korea, Russia, etc., and a budget for construction that's currently looming around 22 billion. And really, the only way here is up. So it's only really the Large Hadron Collider or the International Space Station that can really compare in terms of the vast amount of effort and money and finances and scientists and international collaborations put into a single project. How does ITER compare to JET, the most successful tokamak to date? The radius of ITER's central donut torus, where the plasma is contained, is expected to be about 6.2 metres compared to JET's 3 metres. It will contain 10 times as much plasma as JET did. It aims to multiply the power supplied to its plasma by a factor of 10 compared to JET's 0.7. It will supply 50 megawatts of heating to its plasma compared to 26 megawatts at JET. They're aiming to confine the plasma in H mode for more than 5 minutes, compared to JET's record confinement time of 20 seconds or so. And the current that the ITER tokamak will run through the plasma to pinch and compress it, and prevent it drifting to the edges of the donut in the magnetic fields, will be 17 million amps compared to 7 million in JET. The central device may be only 6 metres in radius, but don't let that fool you. There's an enormous amount of auxiliary stuff, heating mechanisms, superconducting magnets and their cooling apparatus, the first wall, the vacuum chamber that protects the components from damage and so on, such that the whole ITER site will cover nearly a square mile in the south of France when everything is constructed. The wires for the external superconducting magnet coils will stretch out for 100,000 kilometres. That's enough to wrap all the way around the Earth twice and still have some left over. The vacuum vessel that contains the central tokamak will be 11 metres tall and 20 metres in diameter, and it will weigh around 18,000 tonnes. In other words, the device is truly monumental in size. A large part of this is to ensure that confinement time is high enough. Given that confinement time is limited by instabilities and turbulence, When these cannot be reduced further using different, smarter plasma configurations, one way to improve confinement time is to create a larger device with more plasma so that the energy cannot escape as quickly. And that's a large part of how ITER improves on JET. Seeing why this works is fairly simple and intuitive too. Ultimately, the fusion power that's generated depends on the volume of the fusing plasma, while the ability of energy to escape depends on its surface area and its edges. That's where radiation and bursts of particles are ultimately escaping from. The physics, things like the temperature, the density, and the external magnetic fields, sets the rate at which power is generated in the plasma's bulk, and escapes via the surface area. So if you scale things up, that surface area to volume ratio will always get smaller, and you'll always get closer to Q equals 1 and break even. This is why tokamaks and fusion devices have been getting progressively bigger since the cute tabletop devices we first discussed in the 50s and 60s. You get more potential plasma to undergo fusion and release energy, and a smaller surface area by comparison, which essentially gives less possibilities for particles and energy to leak out. But of course, making your devices bigger brings with it a whole host of new challenges. Some of the challenges associated with ITER involve how to drive that 50 megawatts of power into the plasma in the first place. In previous episodes, we talked about neutral beam injection as a method of heating the plasma. You accelerate ions to high energies with an electric field, then you pass them through a nice cloud of electrons where they can pick up another electron and become atoms again. These neutral atoms then don't destabilise the plasma, as much as they would if they had electric fields anyway, and they crash into the plasma ions, passing on their kinetic energy and heating up the plasma. And also helping to drive the plasma current, because you generally shoot them in the same direction as the plasma current, so that the ions in the plasma will preferentially move in that direction. The problem with ITER is that it's so big and has such a large volume of plasma that you need to shoot these particles in at very high energies, so that they can even get to the centre of the plasma, which is where you really want to heat it. The energy that they need is around 1 megaelectronvolt, so that they can penetrate deep enough into the plasma. But at these energies, as you can imagine, it's extremely difficult to make them neutral, as they're too hot to easily recombine with the electrons again. After all, if they have that much energy, then they're basically already going to be ionised in their normal thermal equilibrium state. So ITER's neutral beam heating goes the other way. First you add an extra electron to the atom, then it's negatively charged and you accelerate it to high velocities with your electric fields, and then you can knock the extra electron off, leaving fast-moving neutral atoms that can heat the centre of the plasma. This has never been done on any previous tokamak, so it's brand new technology, but lots of progress has already been made in developing it. Further heating comes from electromagnetic waves, which blast the plasma at its cyclotron frequency. This is the frequency at which the particles basically want to go around the magnetic field, and so it causes a kind of resonance. The ions and the electrons resonate and pick up energy from the electromagnetic waves, which gradually heats them up. To do this, you need big, powerful electrical antenna. Just another example of the auxiliary apparatus that's needed to be around the tokamak to make it work. Even with this level of heating, it's still not entirely clear whether this will be enough to drive the plasma in this much bigger device into the H mode, where the damaging problems of turbulence are suppressed. Try as they might, no one has been able to come up with a closed full theory with all the equations of why H mode plasmas exist, even though the results have been reproduced under a range of conditions at tokamaks all around the world. We simply don't have the equations. Huge amounts of theoretical and computational effort, experimental research at existing tokamaks and so on have gone into trying to reduce this uncertainty to ensure that ITER's design would be sufficient to reach H mode and to understand why it happens, but it still remains just about possible that ITER may not get there. These vast challenges show up in almost any aspect of the device that you care to look at. I mean, similarly, the diverter in the ITER tokamak has to do things that no one else has ever done. A quick reminder of what the diverter is. This is the thing that's at the bottom of the vacuum vessel that contains all of your plasma. The diverter extracts heat and hot particles produced by the fusion reaction, minimises the plasma contamination from melting away at the walls, and protects the surrounding walls from thermal and neutron loads. Since the diverter is essentially having to handle the power that's generated by ITER, alongside being bombarded by a huge flux of radioactive neutrons, the system needs to be incredibly tough. In fact, just looking at the heat alone, around 20 megawatts of power is going to be deposited on every square metre of the diverter. That's 10 to 20 times higher than the amount of heating for space capsules re-entering Earth's atmosphere, and we've all seen things burning up on re-entry. The diverter will essentially be smashed with the most sustained heat and the most sustained neutron radiation of anything that's ever existed on Earth. So creating something that can survive this is a pretty huge materials challenge in itself. The plate is made of tungsten with the highest melting point of any metal, but that won't be enough. We're talking about temperatures of tens of millions of degrees compared to tungsten's puny melting point of 3000 Kelvin. So it has to have a sophisticated system that pumps large amounts of coolant to cool it down. It's positioned at an angle so that it covers a larger surface area, and they're also hoping to tweak the magnetic field to help it cover a larger surface area, spreading the power over a larger area. But there's no getting around the fact that the diverter in ITER is going to have to withstand some unprecedented punishment without melting, and it's a key area of research for the machine to actually perform as planned. Another area that needs to be incredibly robust and sophisticated is the first wall of the tokamak. Remember, this is the interior of the vessel that's supposed to protect the delicate superconducting magnets and the rest of the apparatus, and people in general, from the extraordinary heat and neutron flux. The neutrons that turn pretty much anything they hit into brittle radioactive waste. And those central superconducting magnets need to be cold. If they're not kept below minus 267 Kelvin, then at these magnetic fields they stop becoming superconducting, and if that happens, suddenly you then have resistance in a magnetic coil that's carrying a truly astonishing amount of energy. According to Rafi Kachadorian, who wrote an article about this, one scientist compared the impact of such a failure to multiple jet aeroplanes crashing into the machine. If the first wall isn't up to the job, or if there's some other catastrophic failure to cool these magnets, you could severely damage the reactor and knock it out of commission for months. We've already discussed how difficult it is to test materials against this kind of punishment, because producing neutron radiation of this kind and with this energy is extremely difficult unless you actually have a full-scale fusion reactor. Under normal operation, the first wall should at least be less irradiated than the diverter, as after all, power is supposed to be diverted through the diverter. One problem is, when the plasmas are operated in the stable H mode, we see edge-localized modes. These are the things we discussed in the jet episode, where little bursts of particles and plasma smash out of the edges of the plasma's torus and slam into parts of the first wall. These will need to be suppressed if at all possible. One of the ways that ITER hopes to do this is to spray them with frozen pellets of argon, neon and other noble gases like that. Once you have these pellets inside there, they will effectively radiate away the energy, with their electrons becoming excited and de-excited. Any impurities in the plasma are very effective at radiating away energy, and it will hopefully cool down the edge-localized mode before it can burst out, removing energy from it. But again, this is a new technology that's still being tested, and we don't know, for example, whether it will damage the plasma confinement, although it's getting rid of these edge-localized modes. But disruptions, those sudden losses of plasma stability that cause the plasma to burst out in all directions. Remember, this was the thing that made Jet jump a few centimetres into the air. These could really spell disaster for ITER. The amount of energy that's released in a disruption, after all, depends on how much plasma you've got, and ITER will have more plasma in it than any previous device. The plasma is easily large enough to produce enough energy to melt part of the first wall if there are disruptions. So if disruptions become a regular feature of ITER operation, then it could be in serious trouble. We don't know precisely how the tokamak will respond and how resilient it will be, but you could imagine that if it takes only 3 or 4 disruptions before you need to repair the tokamak, then you can easily see that the frequency of these disruptions will be crucial in how practical any fusion power plant is. Disruptions occur several times a day in machines like Jet when they're running at full experimental capacity. ITER's website, where things are usually quite glossy, suggests that ITER is built to withstand disruptions in up to 10% of its plasma pulses. If you need to replace the first wall, or worse, some other valuable component that it's failed to protect, every few days when you're running the machine, it will struggle to produce power and may never be economically viable, and it will also slow down your experimental campaign by quite a lot. Again, lots of research is going on into ways in predicting and preventing disruptions. If one looks like it's on the way, ITER will probably douse it with lots of these frozen atomic pellets, which will then act like impurities in the plasma, radiate away the energy, and hopefully prevent an explosive disruption from occurring. But the ability to predict and prevent these miniature explosions of plasma, especially when the mechanics of them is not entirely understood, is going to be both a crucial task and a really tricky one. This is part of why ITER's timeline says that it will produce first plasma in 2021, but might take years after this to operate at peak performance. This was also true for Jet, which opened in 1985 and started producing plasma, but didn't operate at its full performance until 1997, over a decade later. Initially, for fear of damaging the machine, ITER will have to be operated conservatively until disruptions are under control, or until they know what the absolute limit would be for operating ITER before disruptions will be really damaging. I imagine they're basically going to gradually jack up its performance until the disruption becomes a limiting factor. And ultimately, this is a new realm for plasma properties. That's the whole point of it. If it turns out that disruptions are more likely in ITER than they are in JET, or more damaging, then the whole project will become about fixing that problem as much as we can. Choosing what to make the first wall out of is also a difficult balancing act. Inevitably, due to edge-localized modes and disruptions and plasma that comes into contact with the first wall, part of it will be eroded away and end up contaminating the plasma. We've talked about how atoms with lots of electrons act like efficient radiators, impurities that radiate away an awful lot of energy, because their electrons can be easily excited, ionized, recombined, de-excited. There's lots of processes going on whereby these electrons can emit photons as radiation that escape. So you might hope to make the first wall out of tungsten again, because it has a really high melting point, but it's not actually ideal, because it has so many electrons, 74 electrons per atom as a heavy metal, that if the first wall contaminated the plasma, you'd lose an awful lot of heating. And that's why beryllium is chosen as a compromise. Beryllium is element number 4, just after hydrogen, helium and lithium. So it only has 4 electrons, which means that it's much less efficient at radiating away the plasma energy. So an impurity that's made of beryllium is a bit less damaging than one that's made of tungsten. But this adds its own problems, of course. The reason you probably don't think about beryllium much is that it's extremely rare, 2 to 6 parts per million in Earth's crust. Rather than being formed directly by fusion in stars, like many more abundant elements, lots of beryllium isotopes are unstable. Beryllium does exist on Earth, is mostly formed when other elements are bashed by cosmic rays or other types of radiation. It's probably a good thing that it's so rare, because it happens to be toxic to humans. Beryllium dust in your lungs will screw them up badly, and thousands of people who worked with beryllium in the early days, in the 1950s and 1960s, have been left with permanent lung damage or even killed. Evidently, like much of the maintenance of the tokamak, which is so highly radioactive you don't want humans going near the centre of it anyway, the exposure to beryllium will be done with robots and remote handling, as it's done in JET at the moment. Beryllium, with only 4 electrons, radiates away the heat in ITER less, and its melting point of 1100 Celsius is still pretty high. Beryllium has another strange advantage too. It produces more neutrons when it's bombarded with neutrons. And this is important for the next major thing that ITER is supposed to be testing. As we've discussed, ITER and JET set records by fusing deuterium and tritium together. But tritium is very rare. Currently it costs around $30,000 per gram, with a half-life of just 12 years, so you can't exactly store it up as fuel either. It's a difficult fuel to find, store and mine. So the aim is to create tritium breeding reactors. A blanket of lithium just beyond the first wall is going to be bombarded with neutrons. This will in turn create tritium, which they can scrape from the inside of ITER, alongside whichever tritium wasn't burned in the initial reactions. And hopefully then your power plant is self-sustaining, creating some of its own fuel. The fact that beryllium then is producing an extra neutron is a good thing, in some ways, because the first wall will produce neutrons that will be absorbed by the lithium, creating more tritium. The central solenoid, that central coil of superconducting magnet that goes right in the middle of the torus and passes through it and actually helps to generate the current in the plasma, is an incredible thing all by itself. There are 6 modules of wire stacked on top of each other which can run opposing magnetic fields. This allows the magnetic field within the tokamak to be shaped in different ways. But it also means that when opposing fields are run through the coils of wire, there's a tremendous force that pushes the coils apart that you have to deal with. This force could be up to 60 meganewtons. By comparison, that's twice the force that a space shuttle requires to take off, just pushing these magnets apart. Niobium tin is a superconducting wire. When cooled, it has 0 resistance and can create astonishingly high magnetic fields, as you need for ITER to work. But this also makes it delicate and fragile. It cannot withstand much punishment from the neutrons produced by the fusion reactions. Once it's drawn into wire, it must be baked into a furnace to become superconducting. And with each pulse, the material fractures slightly. There's a trade-off. The central coil will last longer if the plasma current required to reach the fusion temperatures is less, if it's fired with less energy, that is to speak. But a certain energy is required for the plasma current to reach its goal. Currently, they think that it will be able to run for 60,000 pulses over the lifetime of ITER. According to ITER's website, each one of these wire modules takes around 2 years to manufacture, and they're currently building just 1 spare, along with 6 original modules. Obviously, if something happened that rendered them inoperable, it could take years to get ITER running again. ITER is an experimental reactor. That means that it has a hell of a lot of diagnostics, which are all measuring different properties of the plasma, the current, what's going on with the fusion reactions, the temperatures, the densities, all kinds of things. The central brain of ITER, a computer called Kodak, we'll be processing data from 120,000 different sources to try to monitor and diagnose the plasma performance as it continues, to understand the physics of the fusion reactor and adjust its design in real time to feed back against changes to the plasma if it can. So what is ITER supposed to accomplish exactly? We'll talk about its goals specifically, and we'll talk about its design a bit later. They want to attain a power multiplication factor of Q of 10 or more for sustained bursts of 5 minutes. 50 megawatts goes into heating the plasma, 500 megawatts from thermonuclear fusion. As we've discussed, of course, this power won't be harnessed, and it's also not really a net energy gain when you take into account the losses in the buildings, heating and running the magnets. ITER won't produce net energy, but it is designed to exceed and surpass that scientific break-even, which JET nearly but didn't quite manage to do. This is 30 times more power than any tokamak has previously generated, and the confinement time for the plasma is 100 times as long, so we're still seeing that tokamaks are supposed to improve by orders of magnitude with each generation that's built, but it's taking the generations longer and longer to be built. Its secondary aim is to achieve a Q of greater than 5 while the plasma is running in steady state. To get Q up to 10, the plasma current is generated in pulses using electromagnetic induction, but this can't be used in steady state. Using neutral beam injection to drive the current, as well as the so-called bootstrap plasma current that forms when the plasma current is self-reinforcing, you can sustain the plasma for a much longer time than 5 minutes. This is where ITER is aiming to simulate what a real power plant might be like, something that operates continuously for as long as possible, and the designers are aiming to demonstrate that it can achieve this steady state, and it can still achieve significant power gain. Of course, it's in these steady state runs, where there's just no let-up, that the diverter and the first wall are going to be most challenged. ITER is also hoping to achieve a burning plasma. In a Q greater than 10 plasma, you imagine that a good deal of the energy to heat the plasma will come from the thermonuclear reactions themselves. This might be enough to ignite the plasma. In other words, when you take away the external heating altogether, the fusion would not cease, but it will at any rate demonstrate that the plasma is capable of a self-sustaining controlled reaction if this part of it works. Ignition would be nice, and maybe if the plasma happens to work better than expected, it might just be possible with some specific version of ITER, but it's not the primary goal of the device, which is first and foremost hoping to break even and produce a power gain. A burning plasma, though, is likely to be different even to any of the plasmas that have currently been studied, which is why it would be so interesting. For a start, if you do get lots of deuterium-tritium fusion going, that's good, but it also means for the first time your plasma will have a significant amount of fused nuclei. The product of that fusion, those helium-4 nuclei or alpha particles, will change the behaviour of the plasma once again. In fact, as they hoped would happen for NIF, these helium-4 nuclei should end up becoming the dominant source of energy for the plasma, heating the plasma in the future. So a great deal of the plasma physics effort at ITER will be trying to understand how this new burning plasma actually works. ITER is also hoping to demonstrate that all of the various technologies, the superconducting magnets, the vacuum system, the heating, the diverter, etc., can actually work together. And it's also there to test out the various tritium breeding schemes that have been proposed to recover tritium from the device so that the reactor is more self-sufficient in terms of fuel, and of course to test out the safety characteristics of a fusion reactor. So what you can probably see already is that there are a number of potential ways that ITER has real challenges. What if some new plasma instability is discovered? What if disruptions are more common than we think, or if they prove to be more damaging to ITER's internal components, or if it's difficult to stop them by the mechanisms we have today? What if the heating system fails to deliver that 50 megawatts of power to the central plasma? What if the diverter or the first wall can't stand up to the conditions in the inside of the reactor, or at any rate they need to be replaced so often that getting practical power out of the device looks impossible? And what if tritium breeding is unsuccessful, and the attempts to retrieve extra fuel from the reactor don't succeed? I don't think any of these questions have yet been answered, although places like JET are trying, of course, but that's why it's going to be so fascinating to see how each of these aspects of the tokamak perform, and of course why dozens of smart and dedicated people are working on solving each problem in various countries all around the world. Next episode we'll talk a little more about ITER's history so far, the politics surrounding the project, how its construction phase has gone, and its prospects for the future. Thanks for listening to this episode of Physical Attraction. You can find us on the web at www.physicspodcast.com, where you'll find plenty of things, an archive of all of our episodes, so many now. You'll find the contact form where you can get in touch with us. You will find our PayPal, our Patreon, places where you can get in touch with us there. You'll find all sorts of things. Alongside, you can also follow us on Twitter at PhysicsPod. You can go to the Facebook page, Physical Attraction, and get in touch with us there. Some of the best things you can do to support the show would be to buy some of those old bonus episodes, or subscribe to the Patreon where you'll get those bonus episodes along with your subscription. Or you could just leave us a review on iTunes, or indeed just tell as many people as you can about the show. Every audience member helps. Until next time then, take care.